Hi, let us briefly recall what we have discussed in the slides. Okay, so if we take any physical problem, there are three ways to solve a physical problem. Okay, experimental approach, analytical approach, and numerical, or also this is also called as computational approach. Okay, in experiments, we take a physical problem and conducting the experiments on 1:1 scaled prototype is very expensive. So we develop scaled models and we conduct experiments satisfying dynamic similarity conditions. Okay, so we conduct experiments and then we analyze result. Okay, so the one with the red arrow gives the flow chart of an experimental approach. Okay, but when we come to analytical approach, we take the physical problem and then we develop mathematical model for the problem. By this we mean that we develop governing equation that describes dominant physical features of the problem. Okay, it is usually differential or integral equations. Okay, so most of the physical phenomena are governed by differential or integral equation. Okay, some examples are Navier-Stokes equations. Okay, that govern so Navier-Stokes equations that describes behavior of fluid flows, or Lamé equation that describes the dynamics of a structure. Okay, so we develop mathematical model, then we make physics driven simplifications. Okay, by physics driven simplification we mean the original mathematical models many times may contain so complicated and they contain more information than what we need. Okay, in this case, based on physical details of the problem, we can simplify the equation. Okay, for example, we can simplify the Navier-Stokes equation into boundary layer equations. Okay, so that simplifies the complications associated with the solution of the original Navier-Stokes equation. Or based on the physics of the problem, we can make assumptions like steady flow or uniform flow that will reduce the complexity involved in solving the governing equation. Okay, so after making the physics driven simplification, we employ an analytical approach. It can be for example Fourier series or Laplace transformation or any appropriate method of choice for the particular problem to obtain the solution. Okay, so this orange or arrows represent flow of steps that are usually employed in an analytical approach. Okay, the third one, computational or numerical, which is of our interest. So we start with a physical problem. Okay, we need mathematical model to that describe the behavior of the physical problem. We make physics driven simplification. Okay, so the next step for an computational approach. Okay, so this blue one represent numerical approach. Okay, so we use numerical methods. Okay, we employ numerical methods on the governing equations or the simplified equations that we obtain after this step. Okay, so this physics driven simplification is an optional step. Okay, it may not be there. We can always directly approach the original equation. Okay, so by numerical methods we can say that it has two steps. Okay, one we can call is as discretization. Okay, by discretization we mean we break down the non-linear problem into a series of linear problems, or most importantly we convert PDE, okay, into a system of linear algebraic equations. Okay, so we are going to discuss all these points during this course. Okay, so this is the idea of this lecture is to provide a brief overview of the steps. Okay, we convert the PDEs into system of linear algebraic equations. Computers can handle only algebraic equations, they cannot handle PDEs. Okay, so the next step is the solution of the system of linear algebraic equations. Okay, in the numerical methods course, you have learned techniques like Gauss elimination. We are going to see a few more methods to solve the system of linear algebraic equation numerically. Okay, so in the discretization step, what we are doing is that we are converting the mathematical model into an appropriate form that a computer can handle. Okay, computers cannot handle PDEs. Okay, so this is the core of CFD or any other be it computational fluid dynamics or finite element method for structures. This is the core of any numerical methods. Okay, let's say this is core of CFD, and this contains all the theoretical aspects of CFD or structural analysis. Okay, so once we have discretized the mathematical model, we go on to develop computer algorithms. Okay, so now we have converted the PDE into a system of linear algebraic equation that computer can handle. Now by developing algorithm, what we are saying is we are going to develop or sequence of steps or instruction to the computer that it can follow and give us the solution in an efficient manner. Okay, so once we write the algorithm, we go on to write software. Okay, so we develop codes that can use this algorithm. Okay, so the first this we can say the first step of any CFD or any other numerical analysis is to discretize. The second step is the computer implementation. Okay, once the computer implementation is done, what we need to do is that we need to do verification and validation. Okay, you have developed you have used a mathematical model, you have converted the partial differential equation into a system of linear algebraic equation, you have written a code, and you have got the solution. Now we need to test our mathematical model, numerical method we employed, and we need to check if our computer implementation are correct. Okay, so this step, which we can call as step 3, the validation part, helps us to find shortcomings in any of these steps and help us to improve our model or our program. Okay, so this validation part is of great help in debugging the software that you have developed. Okay, this is a very, very important step. Okay, without verification and validation of the either your discretization or the computer program that you have, the results that you produce will not be acceptable, will not be accepted by the community. Okay, any software that you develop, you need to validate exhaustively with the available experimental results or the well accepted computational solutions. Okay, and the last step is to conduct or the next step is to conduct numerical experiments. And analyze your results. Okay, and analyze your results. Okay, so this is the fourth step of any analysis. Okay, so in general, any computational analysis of a physical problem involves 4 steps. One is the discretization of the governing equation. Second is the computer implementation. Third is that you verify and validate your code. You verify your model and validate your code. And fourth step is to perform the numerical experiments to get physical information of the problem. For example, you're interested in solving flow over a cylinder, you are varying the Reynolds number or any other parameter that you have to understand how the physics of the problem varies with Reynolds number. Okay, so the analysis is specific to a particular problem, whereas the first three steps are common to governing equations. Okay, and in this course we are going to focus on all these steps. Okay, so in this course, okay, focus on all 4 steps. Okay, mainly with the first 3 one, and the fourth one we will briefly discuss towards the end. Okay, so these are the steps involved in numerical or computational analysis of any physical problem. Okay, so let us stop this lecture by discussing our course plan. What exactly are we going to do it, and the roadmap of how we will do it. Okay, now the main aim of this course, as you can understand from the title, is to discuss computational methods for viscous, incompressible, Newtonian flows. Okay, so we are going to develop or discuss computational methods for viscous, incompressible Newtonian flows, and the computational methods in specific what we are going to focus is finite volume method. Okay, you don't have to know what finite volume method is now. We will discuss them during this lecture. Okay, but you should know what viscous flow is, what incompressible flow is, and what Newtonian fluid is. Okay, so that you have to know. Okay, so as you know, the governing equation for viscous, incompressible Newtonian flow can be written like this: del dot u is 0, which is mass conservation, and the momentum equation would be u dot del u times rho minus del p plus del square u plus the body force. Okay, so this is mass conservation. Okay, and this is the momentum equation. Okay, the first term, as you know, is unstudied term. Second is the convective term. This is the viscous term. This is the body force or source term, we can say. Okay, and you know the convective terms are non-linear here. Okay, I will share a link for derivation of this equation. You have to go through it and spend time to understand how did we obtain this equation. Okay, and as you know from your fluid mechanics course, so Navier-Stokes equations are partial differential equations. They are non-linear partial differential equation. Okay, the non-linear term is the convective term here. They are coupled non-linear partial differential equation. Okay, so the analytical solution to this complex equation is not possible. Okay, so we focus on computational method to obtain approximate solution. Okay, so in addition to this, we also discuss heat transport equation. Okay, which is the rate of change of temperature plus convection plus diffusion and the source term. Okay, if you studied heat transfer already, you will be you know about this equation. If not, no problem. We will deal with general equations and discuss about computational methods. Okay, don't bother if you have not yet attended heat transfer course. Okay, so our aim is to discuss computational methods for solving these equations. Okay, but before discussing how to solve Navier-Stokes equations, which are very complicated, we are going to make a lot of simplifying assumption and get what do we call as model equations. Okay, we are going to make some simplifying assumptions and we are going to get model equations. Okay, we are going to discuss now. So we use this model equation as a tool to introduce essential CFD concepts. Okay, so before we introduce this model equation, let us look at the momentum and heat transport equation here. Okay, so the first one talks about transport of momentum. The second one is the transport of heat. We take transport of mass or any other transport equation. It will have a general structure. Okay, so the general structure of a transport equation. Okay, let us say we are considering the transport of the quantity phi. Okay, so it will have this general structure. Okay, so this is the unsteady term. Okay, and this is convective transport. This is diffusive transport, and this is the source term. Okay, this is the general structure of any transport equation. It can be transport of mass, momentum, or energy, or any passive scalar. It will have a general structure like this. Okay, now we are going to make a lot of simplifying assumptions to get several model equations. Okay, so the first one is the most simplified one. We assume steady flow. Okay, which means that the first term goes to 0, and we assume that there is no convection. Okay, so the resulting equation is this one. Okay, convective term goes away because we assume there is no convection. Unsteady term goes away. We will have this diffusive term plus the source term equals to 0. Okay, so this equation is called diffusion equation. Okay, and this governs conduction of heat in a medium. Okay, so what we get is this equation is called this is in general this equation is called Poisson equation. Okay, we have a Laplacian term plus a source term, which is the Poisson equation. Okay, so what we are going to do in chapter 2. Okay, in chapter 2 we are going to discuss finite difference method to solve this diffusion equation. Okay, we will start with finite difference method because it is the most intuitive and the most simple method. Okay, and also that whether you want to study finite volume or finite element, it is always helpful if fundamental ideas of finite difference are very clear. Okay, our understanding of finite difference will be helpful in understanding finite volume as well as finite element method. Okay, so we always start with finite difference method. Okay, so then in chapter 3 we solve the same equation using finite volume method. Okay, so the idea of chapter 3 is to introduce the concept of finite volume method, which has more advantage and it is more general when compared to finite difference method. Okay, and most of the softwares, for example ANSYS Fluent, uses finite volume method to solve fluid flow equations. Okay, in chapter 3 we will discuss finite volume method to solve this very simple diffusion equation. Okay, and as the next step, okay, we assume steady flow, but now we consider convection. Okay, and we make an assumption that the velocity field is known. Velocity field is known to us. Okay, somehow we know the velocity field and we are going to solve this convection diffusion equation. Okay, so in the general transport equation we have only neglected the unsteady term. Okay, all right. Now the focus of chapter 4 is on finite volume method for linear convection diffusion equation. Okay, it is linear because we have assumed the velocity field is known, so that gives rise to linearity of the equation. Okay, and actually we discussed both steady and unsteady in this chapter. Unsteady also we discuss. Okay, our idea is to solve linear convection diffusion equation. Okay, the third one, the third assumption we can go for is steady flow with convection. Okay, so now we assume that the velocity field is unknown. Okay, and for simplicity let's take phi equals u. Okay, so sorry, this is not correct, here it should be phi. Okay, so now we have u dot del u equals to alpha u plus s. Okay, so this equation is called, this famous equation is called Burger's equation, and the convective term here, it is non-linear and it represents or it mimics the non-linear convective terms of Navier-Stokes equations. Okay, so the focus of chapter 5 is on finite volume methods for non-linear convection diffusion equation. Okay, so after discussing all these simplified equations, we will go for, as a last step, steady and unsteady Navier-Stokes equations. Okay, that is our the main objective of this course. Okay, so now let us compare the general structure of transport equation, which is here, and the Navier-Stokes equation here. Okay, there are two main differences or two additional challenges, I would say, Navier-Stokes equation have when compared to general transport equation. One is appearance of pressure. Okay, the general transport equation does not have equivalence of pressure term appearing in the momentum equation, and the second one is the additional continuity equation. Okay, so these presents additional challenges, and the focus of chapter 6 is to discuss how to handle these additional challenges and develop reliable numerical methods to solve full Navier-Stokes equation. Okay, so what we have done is we have taken the full Navier-Stokes equation and we have systematically added one by one some complications, and finally we arrived at we have come to the final objective. Okay, we started with the diffusion equation, then we have added convection with known velocity field, then we have added non-linearity, then we come to the full Navier-Stokes equation. Okay, by making such systematic progress, we can focus one concept at a time and devote our full attention to single concepts at all times. Okay, so this is the roadmap of the course. I would like to stop here by saying that this course is a hands-on course. Okay, it is not just we are not just going to discuss theory. We will discuss theory part, which mainly covers discretization, and then we will have practice programming sessions. Okay, plus a lot of programming assignments. Okay, this is a hands-on course. It's not just theory. Okay, and the idea of the practice programming assignment is not to teach you a programming language, but tune your programming skills to solve CFD problems. Okay, so if you need to brush up your practice with any programming language of your interest, please start immediately. Okay, but we will have some practice sessions to help you write CFD codes using programming language of your choice. In this course we will focus on Python and MATLAB. Okay, so both Python and MATLAB. It's just you don't have to know both, but if you know either one, it would be very helpful for you. Okay, thank you.